All right, Physics 20. This next chapter on work, power, and energy um, ties in together with the circular motion stuff we did this last week to build for the project the following week. So let me go through and talk a little bit about energy, work, and power. I'm going to start with in the context of this roller coaster. Um, Love roller coasters. Not necessarily fearless about them, but they're exciting, and I like to watch people enjoying the rides themselves. I can probably handle the Callaway roller coaster. That's about as good enough for me. But all of them are designed so that you load on the ride, and then a motor lifts you and the carts up to a highest point of the ride. What's happening there is that the roller coaster motor is providing some work to build up your gravitational potential energy, put you to the highest point where all of your energy almost is gravitational potential energy. And then what happens is that you start to fall along the track. And as you fall here, that gravitational potential energy changes into kinetic energy the farther you fall. And then as you rise back up again, that kinetic goes back into potential. And it ends up going back and forth between kinetic and potential as you go around the ride. Now, there's also work done by friction, which is why you can't make a loop that's as high as what your starting point is, because as you go along here, some of your energy is lost due to friction. But you can get a series of loops that get smaller as you go along because you will probably have enough kinetic energy to make it through, even though you lose some energy due to work done by friction. So let's talk a little bit about all of those quantities: work, power. Power is how much energy is produced here to get you to the top. Work, power, kinetic, and gravitational potential energy. So first of all, there are many different forms of energy. In Science 10, you talk a lot about energy, some different forms of energy: solar, chemical, nuclear, heat, geothermal, wind energy, hydroelectric energy, lots of different forms of energy that we can talk about. But in Science 10, there's three that you definitely talk about: gravitational potential energy, work, and kinetic energy. Now, gravitational potential energy, the formula for it is mass times the gravitational acceleration times the height, mgh. So it's really energy due to an object's height above the ground, usually is what we call height zero, is the ground. So gravitational potential energy, mgh. Now, you can actually call height zero whatever you want, but we usually use the ground so that way we're all talking about the same height zero mark. So I've got an example here. An elevator car has a mass of 750 kilograms. There's three passengers, one mass 65, the other 30, the other 48. And the ride goes from the eighth floor to ground floor, which is 21 meters below. What is the change in the gravitational potential energy of the car and its passengers? Well, gravitational potential energy being mgh, we would have to take the total mass times by, whoa, I forgot to include my 9.81 here. Okay. Gravitational potential energy would be the total mass times the gravitational acceleration times the height. Now, you might be wondering why I put a negative on 21, and that's just because we're losing this gravitational potential energy because we're going down. And that's all that negative means. Potential energy is not a vector quantity, but we're just losing the energy. So that's why it's negative. And the units for energy are in joules, capital J. Another example here with kinetic energy. If we look at the kinetic energy of objects, the kinetic energy of an object is equal to 1/2 the mass times its speed squared. So basically, when you think of kinetic energy, you just think if something is moving, it has kinetic energy. Just like with gravitational potential energy, if something has a height, it has potential energy. And so here, a 45 kilogram girl pedals a 16 kilogram bike at a speed of 2.5. What is the kinetic energy of the system? Well, you take the total mass, which would be the 61 kilograms, times by half, times by the 2.5 meters per second squared. And if we're not in meters per second, you got to change it to meters per second. That way we get the standard unit of joules. So 191 joules. I think I'm going to go in and change that and just write it as 191. Not sure why we go times 10 to the second there. Okay, so just a quick example of finding kinetic energy. Now, work is more complicated because there's lots of different formulas for work. One of the formulas for work is just force times distance parallel. So, in other words, if you're lifting something, whatever force you apply to that object times however far you lift it. If you talk about the work that you do when you're pushing yourself forward, whatever force you apply in the ground times by the distance that you travel. Sometimes, like when you're pushing a lawnmower, where you have an angle, the handle of the lawnmower makes an angle with the ground. Sometimes there's an angle between your force and the distance that you're going. So, in other words, you push down on the handle of a lawnmower, and the lawnmower just goes straight horizontally. So, even though there's an angle between the handle of the lawnmower and the ground, there's still work being done, and it's just force times distance cos theta. And the third formula is work is change in energy. So anytime you have a change in energy, it's associated work being done. So that change of energy could be kinetic or potential. But as soon as you have any change in kinetic energy, work is being done. For example, as soon as I pick up a baseball, as soon as I lift it up, I've changed its potential energy. I've created work. I've done work. Then as I throw the baseball, my work goes into kinetic energy of the baseball and gives it some kinetic energy. But work is done in both lifting and throwing something. So a couple of examples. A cable of a large crane applies a force of 22,000 newtons to a demolition ball. As the ball is lifted vertically a height of 7.6 meters, how much work does this force do on the ball? Well, because the force is up and the distance is up, we don't have any angle between the two. We just can multiply those two numbers together to get the final total work done. On the other hand, example 2, if a student is using a push broom uh, and exerting a force of 20 newtons to push a broom 30 meters across the floor, but the broom itself is set at a 70-degree angle to the floor, and then if you're looking for the work done, well, your force and your distance aren't entirely in the same direction. As a matter of fact, there's a 70-degree angle between them. And so then we use the FD cos theta formula. We still take our force times by our distance, so 20 times 30, but then we have to multiply by the cos of 70 to get the full work being done. Third example, back to our roller coaster example. A roller coaster ride lifts all its mass with passengers, and the total mass there is 7,200 kilograms from rest at a ground level to a height of 45 meters with a speed of half a meter per second. How much work is being done? So if I go back to my picture, maybe we're loading the roller coaster way down here, and you're lifting that roller coaster all the way up to here. And we're trying to figure out how much work is done to take the passengers from rest to this height here and give them a little bit of a speed there. So in that case, the work that we're doing is going to be a change in energy. We're going to change the kinetic energy because when you're on the ride, it doesn't start as you're loading it up. You get loaded up and you don't have a speed. But at the top, you're going to have a little bit of speed, in this case, half a meter per second. But most of your change in energy is going to be the potential energy you build up because we got you and as a passenger on the roller coaster and all of the carts in the roller coaster a height of 45 meters. So the work here is a change in energy. It's both kinetic and potential. So to find the kinetic, we use 1/2 mv squared. To find the potential, we use mgh. And then you add them together to get the full work, which is 3.2 times 10 to the 6 joules or 3.2 megajoules, 3.2 million joules. Huge amount of energy involved in lifting that roller coaster to the top. And that builds all of its energy so that when you see into the next section that we talk about here, all of that energy is going to be transformed into potential and kinetic as the cart rolls around with the passengers in it. What's power? Power is the last one of these that we're going to talk about. Power is just the rate at which energy is used. So it's a measure of joules per second. So if you buy light bulbs and you got a 60-watt bulb and a 100-watt bulb, well, the 100-watt bulb is using more electric energy per time than the 60-watt bulb. And usually that means that it's brighter, unless it's a poor light bulb. So the higher the watts, the more electric energy the object uses. So here's the same type of example of the roller coaster ride. Lifting the 7,200 kilogram cart and passengers, a height of 45 meters with a speed of a half meter per second. How much work is done? And if it takes 50 seconds, what's the power rating that the lifting motor has to have for that roller coaster? So here we go through and we can find the work being done. Then, if we're trying to figure out the power that it uses, we can just take the work, because that's the energy that we've produced with that motor, and we divide it by the time of 50 seconds. And it changes the 3.2 million joules to a watt rating, in this case 6.4 times 10 to the fourth watts, or if we change that to kilowatts, that'd be 64 kilowatts, or 64,000 watts. Give you an idea how strong of a motor you'd have to have. Now, some of you might be familiar with horsepower. Horsepower is very familiar to those that are mechanically minded and thinking of vehicles and uh, other lifting devices. A horsepower is a power rating. And what it is that 1 horsepower is equivalent to 746 watts. So if you were, trying to tie this back to horsepower, that's the conversion, is that 1 horsepower is 746 watts. Anyway, on this handout that I have, I've got a few extra questions with their solutions there. I'd like you to try to do those. Take a picture of your completed work and send it back to me. Thanks.